the T distribution. This is after discussing the Z distribution in the previous lecture. We don't need to go directly to the T distribution. And as you see from this slide, we have a certain formula for Z, and we discussed it previously. But in the most real-life situation, the variance of the population is unknown. And this is a fact, actually, because the actual variance is unknown. Why? Because we are dealing with a large number of samples, not a large number of individuals, and we cannot cover them all. But we know that Z score is equal to x minus mu over sigma divided by square root of n, or the standard error. From this formula, we can obtain the Z value. And this Z value is normally distributed if the population is normally distributed, and is approximately normally distributed when the population is large. But it cannot be used because sigma is unknown. This is the main situation, and this is the main fact, that mu is not found. How can we deal with such unknown sigma? The sigma is unknown. This is the main thing that to be dealt with within the T distribution. Now I would like to remind you with a certain formula that has been used previously, which is the standard deviation. And as I told you, the standard deviation is just only the square root of the variance. The variance is denoted as s square, and if we take the square root of square, it will yield s. And if we take the square root of the variance is summation xi minus x bar square over m minus 1. This is the main formula for obtaining the standard deviation, and we actually took a lot of examples related to the standard deviation. And just to remind you that we have, if we move above or below the standard, the mean, the overall mean actually of the population, 1 or 2 or 3 standard deviation units, and we go further in the discussion for obtaining the Z values and also the confidence limits, the upper and lower confidence limit, just only to predict the overall mean of the population in general. This standard deviation can be used to replace sigma, actually, because sigma square is the whole population variance. Now if you take the square root of the sigma, it will equal to sigma, just only sigma without squaring. So it is the standard deviation. So if n is larger or greater than or equal to 30, then S, which is the standard deviation, is a good approximation of sigma. This is an alternative procedure is used when the sample's variance is unknown. It is known as student t-test. This is the main formula, just to replace sigma with S. S is the samples, the drawn samples from the whole population. We took, or we calculate the standard deviation for it, just taking the square root of calculating the square root of the variance. So if the population, now this is in one condition, greater than or equal to 30, the number of samples, and we can replace S instead of sigma. And this is the main condition, just only to be used, and this thing is called as student t-test. Student t-test. Now student t-test here is used as an alternative for what? For Z values. Now Z scores, or with small samples, cannot solve the large samples, because the sigma is unknown in the assumption. It uses the following formula, just only to calculate the student t-test. It is the same as Z, but here we replace sigma or S instead of sigma. So T equal to X minus mu over S, or the standard deviation of the standard error, the standard error of the selected or represented sample, which R should be more or equal to 30 samples. So it is the same as Z, but here we use S instead of the standard deviation of the samples that are more than or equal to 30 over the square root of the number of the samples. Now, student t-test, as you see from this picture, it was developed in 1908 by. After that, the T distribution become obvious after publishing his paper, and now we have some certain properties of the T distribution. The T distribution mean should be equal to 0. It's symmetrical about the mean. What do you mean by symmetrical? It is معناته متناظر. It is symmetrical about the mean. It means the above, if you go above and below the T distribution, they will be the same as a mirror. Together. Just really, imagine with me that we have a normal distribution curve, and we have the tails, the right and the left tail. They are the same. If we pick them together and put them together around the mean, they will be the same. They are symmetrical. Variance is greater than 1, but approach is 1 as the sample gets larger. Now, if you see from the third property right here of the T distribution, it is greater than 1 usually, but if the sample size is very high, very large, actually it will be approaches to 1. For the degrees of freedom is which are more than 2, the variance equal to degrees of freedom over degrees of freedom minus 2, or the variance is n minus 1 over n minus 3. This is the main idea behind the degrees of freedom. Degrees of freedom here is in Arabic we call it درجات الحرية. And usually the degrees of freedom give us the number of comparisons that can be made between the treatments actually. If we have, for example, 3 treatments, okay, we can compare the first with the second and the first with the third. And usually if we have 4, we can compare the first with the second, the first with the third, the third with the first with the fourth. It means the 3 comparisons that can be made between the 4 treatments, and 2 between the 3, and 1 between just only 2 treatments. So usually the degrees of freedom is just only subtracting the number of observation minus 1. So the variance of this kind of informations, and this just only to approach the 1 is n minus 1 over n minus 3. The number of observation n is referred to the number of observation used in the study. So also the range is from minus infinity to infinity. This is the range of it. It is unlimited number. T is really a family of distributions, because the divisors are different. Compared with the normal distribution, T is less peaked and has higher tail. So if you imagine with me when we took or we discuss the T distribution or the normal distribution curve, now imagine with me the T distribution is less peaked than the normal distribution and has higher tails. You can imagine with me the tails, the right and the left tails that observed in the normal distribution, and also the same for the T, but it is less peaked. T distribution approaches the normal distribution as n minus 1 approaches infinity. So by using a large number of samples, the T distribution approaches the normal distribution. No, this is the same condition. The one condition that can be used just only to compare as the T distribution to be as the normal distribution. The condition is just only to use infinite number of observations. So this is the main idea or the main properties for the T distribution. This is the student T distribution. As you see, imagine with me that we have those information. It is less peaked than the normal distribution. If we use, for example, from here point 1, point 2, point 3, point 4, this is the distribution of the it will be higher. As I told you previously, it is less peaked than the normal distribution. It will be reached the normal distribution when by using large number of observation, and it will be the tails are higher. You can return back to the previous slide, and you can just only to understand this curves. Just only the thing behind those peaks actually, the color, the green one with the others, and it will be higher. It will be more higher by using much more samples. Okay, and you can see if it is higher, it will be narrow, not wide. It will be reached as, it will be treated, if we use large number of observation, it will be treated as normal distribution. The confidence interval for the mean using T distribution, as we've used in Z distribution, general relationship as we see previously, it is the estimator plus minus the reliability coefficient times or multiplied by the standard error. This is the same idea, the same formula that used in the Z distribution, but here we are using T tables rather than using Z tables. Reliability coefficient is obtained from the T distribution in general. So the confidence interval here, when sampling is from a normal distribution whose standard deviation is equal to sigma and unknown, the 100 by 1 minus alpha % confident interval for the population mean mu is given by x bar plus minus t to 1 minus alpha over 2, okay, times the standard error, which is the standard deviation over the square root of the n. Okay, so this is the main formula that has been used. If you return back to the Z distribution, you can see the same formula, but here we use T distributions rather than using the Z distribution, the Z values actually. Now we have two distributions actually. How can we use them? How can we decide to use Z or T distribution in our experiments? When constructing confidence interval for a population mean, we must decide whether to use Z or T distribution. Which one to be used? It depends on the size of the samples, whether it is normally distributed or not, and whether or not the variance is known. There are various flowchart and decision keys that can be used to help the decision or to decide. Actually, mine will go in the second flowchart in the following slide. Now, from this slide, you can see that how can we decide whether to use Z or T? Just it depends on the size of the sample. This is the first one. Whether it is normal distributed or not, this is the second one. Whether or not the variance is known or unknown. Those are the major three things that to be used in the next flowchart. Again, the size of the samples, normally or non-normally distributed, and known or unknown variances. This is the main chart, which is key for deciding between Z and T in confidence interval construction. First of all, we do need to look for the population, the normality of or whether it is normal distributed or not. Not as above normal distributed. Population normal distributed, we go to 2. Okay, which is 2. This is the second 2. Here, the numbers in the right hand here is the second step. Second 1, 2, 3, 4, which are in the left hand. So population normal distributed will go directly to the number 2, which is sample size is large. We do need to check it whether it is 30 or less than higher or lower than 30. If it is not normal distributed in the first one, we go to the fifth step here, which is size sample is larger or the sample is less than 30. Okay. Now, if you go to the second one, the sample size is large. We can go moving directly to the third step, which is population. We do need to think about the population variance, whether it is known or unknown. If it is known, we use Z. If it is unknown, we use T and or Z. We have the option to use both of them, whether it is known or unknown. But if it is known, we can go directly to Z without using t-values or t-distribution. Now, population variance is unknown or known, use z, and not known, use t. Okay? The variance now. The population is known, t. Population variance is unknown, use t. Sample size is large, you go directly to the population variance to see whether the population variance is known. If it is known, we use z, and if the population variance is not known, use t. As you see, sample size is small, that must be go to the 7, which is must be a non-parametric method. If it is large, go directly to test the known or unknown variances. Okay, if it is known, use z, unknown, use t. Now, the main idea from this chart, you can go and to understand it in a better way, in a good way actually. The population, we do need to think about the population, normal distributed or not normally distributed. If it is distributed, you go to the further step, the second and third step directly. Now we do need to think about the sample size and also the known or unknown variances. Those are the major things. The most important one here is the variance, whether it is known or unknown. Known, go to use z table, and unknown, use t table. You can understand this chart just only by using the numbers that is illustrated in the right and the left hand of this chart. Okay? Okay. Now we have an example. In a study of Kamsky and another person found the mean systolic blood pressure of 10 healthy non-pregnant women to be 119 with a standard deviation of 2.1. Now, this is a study that has been conducted by certain researchers. Those researchers deal with the systolic pressure, blood pressure actually, systolic blood pressure. You understand the biological things behind systolic and blood pressure in the heart actually. They took 10 healthy non-pregnant women. So in here is 10, and their mean is 119 and standard deviation to be 2.1. They calculate this thing by using the formulas that has been discussed previously. So the things that to be understood, or for you just to understand this equation or this example, they are: the n is 10 and the mean is 119, and the standard deviation is 2.1. So development of hypertension, albuminuria or edema between 20th week of a pregnant and the first week postpartum. Okay, as you see, eclampsia is a coma and or seizures in the same of the period without other etiology. This is something related to their trial actually, and something biological things that has been studied in their example. So, what's the estimated standard error of the mean? Construct a 99% confidence interval for the mean of the population from which 10 subjected may be presumed to be random samples. What is the precision of the estimate, and what assumptions are necessary for the validity of the confidence interval you construct? The solution, we do need to summarize the values that are obtained from the question or the example. We have 10, n is 10, x bar is 119, and standard deviation is 2.1. Just go directly and draw the sketch for this example. As you see, we have, this is the t-distribution or normal distribution. We are dealing with, the question here is just only 99% confidence interval. He asked about 99% of confidence interval, as we discussed in the Z, remember, in the Z table, Z distribution, the confidence x bar plus minus reliability factor times the the other thing, standard deviation or standard error actually. So if we go to this chart, I'm looking for the 99%. Okay, we are dealing with this shadowed area. Okay, we are dealing by 99%, which is 1 minus alpha equal to 99. It means 1 minus 0.99, it means 1.01. So 0.01, if we divide it into two parts or two tails, it will be alpha over 2 and alpha minus alpha over 2, and it will yield 0.05. This is how can we explain this this figure. The t-value is here. This is the shaded area. This is the targeted area, actually, the line one. Okay. We do need to go for reading the t-table. As you see, this is the t-table, and those number is degrees of freedom. This is the first column. This is the degrees of freedom. Degrees of freedom is usually the number of observations minus 1. Okay, and you can see the t values. Whether when it is 1, it will be yield this one at t.9, t.95, t.975. Okay, t value at different levels, different significant levels, different confidence levels. Okay, and you can go through whether if you use 10, for example, you can see that 10 is crossed with the significant level. We are dealing now with the 99%, which is the second, I think, the second one. Okay, or the third one. Actually, this is the third one, and we have 10 samples. Just only cross-stabbing the 10 with the t of 0.99, and you will yield the value of the t distribution. This is another one, percentile of the t table. As you see, t distribution actually, when using just only p is 0.975. Now we have degrees of freedom, as you see here, t value at 0.9 confidence, 0.95, 97.5, and 99. T99, this is the third one in our example, and we have 10. The number of observation is 10. This is the degrees of freedom. 10 minus 1 is equal to 9, and we can cross-tab 10 or 12 or whatever the number we have here with the confidence level that we are looking for. Here we have 0.99, and the 10 is the number of observation or the degrees of freedom used. I told you the degrees of freedom is just only the number of comparison that can be made between the different samples or different treatment. Now we do need to calculate the standard error. Sorry, we have a standard deviation just only divided by square root of the n, which is here n equal to 10. Okay, s is 2.1 over square root of 10. It will yield 0.664, and just only apply the equation. We have the x bar. X bar in our example is 119 plus minus 3.24. 3.2 here, we took it from where? From the table. Okay, we took it from the table. If you return back to the table, you will find 3.2498. We took it directly from the table times what the standard error that has been calculated from the first step here, and the confidence limit for the hypertension in this example is 119 plus 3.2498 times 0.666 and or the lower limit will be minus, or 119 minus the result of the right multiplication values. Okay, result, sorry. So it will be 116.84 and 121.16. Now we are confident by 99% that the average of this thing or this biological hypertension will be located between 116 and 121. This is how can we interpret our results. The precision here, as you see, the precision as we discussed in the z values, just only the right hand side of the equation. The main equation is x bar plus minus linearity factor in general, which is the t values times the standard error. if we can multiply the reliability factor that obtained from T table times the standard error, it is the just only without the mean. Actually, it is the reliability factor. This is just only the reliability factor that has been obtained for this question. Assumption: the population is normal distributed. 10 subjected represent a random sample from this population. Okay. Now, confidence limit for the differences of two population means. Now, we took just only one sample. Okay, if we have just only one population, and now we need to deal with two populations. How can we obtain the differences between two population means? We have actually the confidence interval for the two population means. From each of the two population, an independent random sample is drawn. Sample mean is for the first population will be x1 bar. The second population will be x2 bar. We can calculate them actually for the two populations that we are targeting. This is a general revision for you, just only to know how can we obtain the z or the t values, x bar minus mu over standard error. Properties, as you see, this is a repetition actually. Repetition values, it has been discussed previously. Okay, this is the percentile of the t distribution. Degrees of freedom from 2, the lowest peak, minus 3, the highest peak. As you see, if you increase the number of observations, the t value of the t distribution will be reached the normality or normal distribution. It has been discussed. You can go back to my discussion. This is another one, confidence interval using t. This is actually repetition. It has been discussed previously. Just to look for this slide and you can read them well. Now we have an example, also another example, the evaluation of the effect on the job body mechanics instruction on the work performance of a newly employed young worker. They have two groups. Now we have two groups, experimental and control group. Now we are dealing with two populations. The experimental group received 1 hour of back school training by the therapist and control didn't. So we do need to compare those two groups. One have a back school training with therapist, and the other didn't have this therapist or the training. So we do need to compare them with each other. The 15 control subjects made a mean of 11.53. Now we will talk number of observations is 15 in the control group that didn't have or receive any training by the therapist. The mean of them, the average for them is 11.53 with a standard deviation of 3.681. They assume that these 115 controls behave as a random sample from population of similar subjects. This is the main assumption to be normal distributed. We wish to estimate the mean scores for the population. So we have N is 15, mean is 11.53, and the standard deviation 3.681. 11.3 is the point estimate of the population mean. Population standard deviation is unknown. We will assume that it is 95% confidence. We will use 95% confidence interval. Okay, so we have the mean estimator of the standard error, which is the standard error, which is the standard deviation over the square root of the number of observation. It means 3.681 over the square root of 15. It will yield 0.9504. Now we need to find the reliability coefficient with confidence interval of 95. Now we are targeting 95 confidence interval, not 99 as in the previous example. And degrees of freedom is 15 minus 1. Now we are dealing with 14. Usually we subtract 1 from the total number of observation and go directly to the degrees of freedom in the first column of the T or Z values or T tables actually. So the confidence interval leaves 0.025. Why 0.25? Because we are dealing with 95%. 95% على الأطراف in the two tails of the normal the T table actually will leave 0.025. The second one 0.25. by summation of both of them, it will be 0.05. In addition to 0.95, it will be the total number, it will be 1, which is the whole surface area below the curve, which is 1 actually. Now we are dealing with the 95. The shaded area will be 95%. This is the targeted area. Okay, so the reliability estimate here can be directly calculated. Confidence interval, as you see here from the right. If you go to the table, you can see 0.025 T 025. 025 it just only take one tail, okay, from the T table. If we subtract them all, it will be 2.1448. Now construct the 95% of confidence interval. We will have the mean 11.3.53 actually, plus minus 2.144. From where we get it? 1.44. We get it from the table, times the standard error. Standard error here is 1.9504. We take it from the dividing just only the standard deviation over square root of n that has been previously calculated in the previous steps, and we can obtain finally the plus minus the standard deviation plus minus the precision, which is our limit of the confidence interval here 9.42, and by addition of this 11.53 plus the product or the result of multiplying reliability factor times the standard error, it will yield 13.57. How can we interpret this thing? By just we can say that we are confident by 95% that this is the mean is located between those two values. And thank you all. Conclusion, as I discussed previously. Many thanks for listening, and hope to return back and listen carefully to my discussion, just only to understand all the process. And if you missed something, you can return back to the Z table that has been discussed actually extensively, okay, and you can understand everything. But here we use T value instead of using the Z values. Thank you very much.